So let's illustrate an application of cross products to computing the area of a parallelogram. Now this is most useful in 3 dimensions when it's difficult to get a good sense of where all of the corner points are at some weird angle in 3 space. But to sort of confirm that everything is working as we expect, let's take a nice simple 2-dimensional example that we would be able to compute without cross products, and then use the cross products to confirm that we get the same answer with that technique. So suppose we have a parallelogram here, and let's suppose we have a base of length 6, and the left side is length 5. Now this is not a rectangle, so we know the area is going to be less than 30, right? This would have to be at right angles to give us an area of 30. What really matters here is the height perpendicular to the base. So if we take from, say, this corner here, and we drop an altitude to the base, and let's just suppose that that height there is 4 for the sake of computational simplicity, then the area would be the length of the base times the height. That is 6 times 4, or 24. So we know that the parallelogram that I have described has an area of 24 square units. So we'll put that in our back pocket and come back to that in a moment and make sure that everything works. Like I said, though, we want to try computing this with the methods presented in this section regarding cross products. Well, if this is a right triangle, we know that this is a 3, 4, 5 triangle. And we need to know this because to use the method of cross products, we need to have 2 vectors describing the parallelogram. So we choose 2 adjacent vectors. Let's take them co-initial at this point right here. And the base is 1 vector that is moving directly to the right. So let's call that vector 6, 0. If you imagine, if you place this within a coordinate system and you put this point at the origin, we have this position vector here, right? That would point at the point 6, 0 on the x-axis. But we don't need that coordinate system. We can just say, okay, this is moving to the right. We go right 6 units, don't change vertically. For this diagonal here, we'll have this vector, and we see that we're moving right 3 up 4. So that vector would have components 3, 4. And remember, the claim from this section is that the magnitude of the cross product will give us the area of the parallelogram. And this follows from, if you compute the area of the parallelogram based on, trigonometry with an angle here, and compare that to the geometric characterization of the magnitude of the cross product, you'll see that they are algebraically equivalent. So let's compute that here. We will need to take 6, 0 crossed with 3, 4. However, the cross product is a 3-dimensional thing. The way I have written this, it does not directly work out. There is an interpretation of this that does, however. If we write this, for example, this 6, 0, another way of writing this is 6i, and 3, 4 is 3i plus 4j, so put an equals here. And we can leave that in that form, or we can say, okay, we want to take a cross product. We need to interpret these in a 3-dimensional setting. So that initial vector 6, 0 can be thought of as being embedded into R3 as 6, 0, 0, right? We can interpret that parallelogram as simply being in the xy plane. We can set the z coordinates to 0, or any other constant we want, but 0 is simplest. And then the second vector would be 3, 4, 0. So we see that what we're trying to do is compute the cross product of 6, 0, 0 with 3, 4, 0. And there are at least 3 ways of doing this, 2 of them based on determinants. And I'll walk through those here. Hopefully you've already read an example in the textbook about these, but I will still try to explain all of the essential details here. To interpret these in terms of determinants, we use them to build a 3x3 matrix. And it's perhaps not technically a matrix, but it has the form of one. I say it's not technically a matrix because when we define a matrix, it needs to be over a particular field, such as the real numbers. But I, j, and k are not real numbers, they are vectors. So, but these here, these other components, are real numbers. So there's this legitimate question of what kind of matrix is this even? What would this mean, right? We'll not worry about that. We'll just say, okay, suppose this is a 3x3 matrix, and we just find our determinant as we normally do. There are at least two common ways of finding determinants of 3x3 matrices, and the first is with the method of cofactor expansion. If you remember cofactor expansion from pre-calc, for instance, you know that you choose any row or column about which to expand, and we customarily choose the first row because of the ijk vectors. It groups things kind of how we want, so I'll do that on this first one. And there's this alternating plus minus plus pattern. And the idea here is that for each term in turn, we multiply that term by the determinant of the matrix that would result if we delete that row and column. So starting with I, we would imagine deleting the first row and the first column that contain I, and you see we'd be left with this matrix 0, 0, 4, 0. So we have I times the determinant of that matrix 0, 0, 4, 0. Okay. Again, we're looking at I, so we delete that row and that column, cover them up, and you see that you're just kind of left with this little 2x2 here, so that's what we have. Next we move on to j, but we alternate signs, so this has to be minus j, and that will be multiplied by the matrix we would get if we delete that row and that column, the row and column containing j. And there we see we have 6, 0, 3, 0. 6, 0, 3, 0. And finally we have plus k. So we have that. We delete that row and column, and we see we have 6, 0, 3, 4. 6, 0, 3, 4. I was drawing those lines to delete them to illustrate what we were doing. Of course, you probably wouldn't want to do that in practice because, you know, if you're writing in pen or pencil, now you have those marks, and by the time you get to the end, everything is all marked up, and it's hard to keep track of what you're doing. But just visualize it, or maybe you know, put your fingers over rows and columns, or however you want to do that. But we get this. This is our first, you know, these here are called the ijk, in this case, are cofactors. They're being multiplied by minors. This is an expansion about the cofactors, or cofactor expansion. Now we have taken this 3x3 determinant and reduced it to a problem of solving three 2x2 determinants, which might sound worse at first, but actually 2x2s are really easy to compute. We could use cofactor expansion again, but more commonly what we do is a standard shortcut where we look at the product of the main diagonal and subtract the product of the back diagonal. So the main diagonal, we have 0 times 0, and we subtract the product of the back diagonal, which is 0 times 4. Now, unfortunately, this particular problem has a lot of zeros, so it might not be the best example. I think I might put together another video illustrating one where all of the entries are different. It might make it a little bit easier to follow if you would like to see an additional example. But this does work for us for right now. We have minus j times, same deal, forward diagonal gives us 6 times 0. We subtract the backward diagonal product, that is 0 times 3, plus k times the forward diagonal is 6 times 4, minus the back diagonal is 0 times 3. Okay. And now it's just a matter of simplifying all of these things. 0 times 0 is 0, 0 times 4 is 0, 0 minus 0 is 0, we have 0i. Again, we have 0 minus 0, so we have minus 0j, or plus 0j, it doesn't matter which way you write that. 6 times 4 is 24, minus 0, so we have plus 24k. Or when we simplify this, we simply have the vector 24k. Now what we wanted was the magnitude of that cross product. So we take the magnitude of, what did we have, 600 cross 340. So that is the magnitude of 24k. And you can evaluate this a couple of ways. One way, of course, another way of writing this is 0, 0, 24. So you could think about your 0 squared plus 0 squared plus 24 squared, take the square root, but it's just going to be, we have just this one component. The magnitude of this will be the absolute value of that coefficient, right? So it'll just be 24. So there we have our 24, which you'll recall is what we already know the area should be. So this cross product business worked out here. Now, of course, a natural impulse is, well, we know the area is 24. Why do we go through all of this? Two things. First off, I wrote a lot more here than is strictly necessary to show you what I was doing step by step. With practice, you can do this faster. And secondly, as I mentioned, this was a very simple example in 2 dimensions. We wouldn't normally use cross product if we know all of the, a full description of the parallelogram in just 2 dimensions. But, if we are working in a 3-dimensional setting and you have some weird parallelogram just floating at some crazy angle in space, well, then it could be a lot harder to figure out, wait, if we drop an altitude from one vertex to the base, how long is that? Where is it going to hit? What is the right angle to that line anyway? Like, doing that geometrically in general could be a serious pain. But if we have the, if we know the coordinates of just 3 of the vertices of the parallelogram, then we can find the 2 vectors that are adjacent, take the cross product of those 2 vectors, which is might look a little cumbersome at first, but with a little bit of practice, this becomes a reasonably straightforward computation, and that's going to be a whole lot faster and easier than trying to do all of the detailed geometric analysis. Now, as a quick side note, if you do remember cofactor expansion from a previous class, you might recall that when we're just working with ordinary matrices with a bunch of numbers, we will most commonly choose a row or column with as many zeros as possible. And if you are comfortable enough with that here, you can save yourself some time. At this step from here, you might, instead of expanding about the first row, as we did, you might instead say, oh, hey, if we expand about this last column, that's going to be a whole lot more efficient, right? We have plus, minus, plus, minus, plus. So you could say, all right, well, we have k times the associated minor, which is 6034, plus 0 times some stuff, which won't matter because that's 0, plus 0 times some stuff, which won't matter because that's 0. So then we just have, the 6 times 4 is 24, minus 0 is 24, times k, and that's a whole lot faster than going through all of these things. If this was less comfortable for you, don't worry about it. I'm just saying, if you are comfortable with determinants from before, you can still use those techniques here. They still work. You could even expand about this second row, because that also has 2 zeros. But you have to remember the appropriate patterns, right? If this is plus, that's minus, plus, minus. So this would give you a -6 times this business with, let's see here, we would have -6 times jk40. So we have -6 times j times 0 is the 0 vector, and then minus 4 times k. So we have -6 times -4 is a positive 24. We still get the 24k. But this is a little bit stranger. I would probably only recommend choosing a different expansion if you have, say, a column that is just 2 zeros and one of the unit vectors, expand about that column and you'll be in good shape. But again, if you don't already know how this stuff works and that was just confusing, don't worry about it. You can just always take the ijk. That's what this textbook does when it expands things. That's what I'll do also when working through these with cofactor expansion, because we want the answers grouped with I, j, and k, right? We would rather not have little vector, little matrices like this where j and k are mixed into the same thing like that. That's less convenient. We want to separate out the I, j, and k components. So that's how we will usually take that. So that is one way of evaluating this thing. Or actually, it's a few ways, but it's the one method of evaluating a determinant by cofactor expansion. You can choose different rows or columns to expand about. I recommend just taking the first row, unless you're more comfortable with this. And then we just expand and simplify and go from there. Again, I wrote out every little step here. With a little bit of practice, we can do a lot more mentally, but you should always at least write down some things. Don't try to do too much. Write down numbers. Keep them, write them down. One of the easiest mistakes to make in a cross-product problem is a sign error or a multiplication error, right? And that usually doesn't happen in the moment when you're doing it. It usually happens if you compute something and you just try to hold it in your head, and then you come back to it and you realize that, well, you don't usually realize it's the problem. You have forgotten something about it and you misremember it and don't realize it and continue on. So do make sure to write down enough to support your memory so that you don't have to worry about forgetting anything, and also enough so that if I'm grading work, I can see what you did, so that if you made a mistake, I can give you partial credit, right? If you just write down an answer and it's wrong, that's going to cost a lot more points than if you write down some steps along the way and I can say, oh, I see, you just made a sign error here, -1. So it's in your best interests for two reasons to write down as much as you can. Or rather, as much as might be useful, let's put it that way. I mentioned there are other approaches to evaluating determinants. So let's rewrite that 3x3 determinant we had. ijk 6 0 0 3 4 0. Now, there is something that is, where do I want to stick this? I guess I can write it over here. There's something that is sometimes known as the rule of Saros, or Saros's rule, or the Saros's scheme, or all kinds of various names for this. And it's kind of an extension of the pattern we had for the 2x2 matrices. To take a 2x2 determinant, again, we can take the product of the main diagonal, or the forward diagonal, and we subtract the product on the back diagonal. Now, it would be nice if we could do that here, but that pretty clearly won't work, because if you just take the product of the main diagonal and subtract the product of the back diagonal, there are, write this out here, if we take the product of the main diagonal and we subtract the product of the back diagonal, that leaves us with 4 entries that we haven't even used, right? So that is unlikely to work. There is a method that is similar, this rule of Saros, but it's slightly more complex. We have to take the 3 forward diagonals and the 3 backward diagonals. Now you might say, well, what do you mean 3 forward diagonals? There's this 1 forward diagonal, but then the next forward diagonal would kind of stop. We hit the edge. Now, if you think about this with what is technically known as toroidal geometry, or a toroidal topology, more informally known as Pac-Man geometry, if you think of some video games where if you go off one side of the screen, you appear on the other side, we have that kind of wrapping around going on, right? So from the diagonal from K goes forward over to here, right? So it sort of wraps around. That can be weird to keep track of, so many students find it much easier, instead of trying to mentally wrap around, to recopy the first 2 columns of your 3x3 matrix. So the first column, we have I, 6, 3. The second column, we have J, 0, 4. Now once you do that, that allows us to write all 3 forward diagonals and all 3 backward diagonals. So we take the forward diagonals here. I'll try to do, I don't want to do this. I'm trying to write this in a way that doesn't make things too hard to see. So we'll come through here. And we'll take the product of the forward diagonal. In this case, that is 0i. 0 times 0 times I. And then we take the product of the next forward diagonal. We have j times 0 times 3, that is 0j. And we'll take the product of the next forward diagonal. K times 6 times 4 is 24k. So we have those 3. Now we take our 3 backward diagonals. Right? We have k times 0 times 3, that is 0k. We have I times 0 times 4, that is 0i. And we have j times 6 times 0, and that gives us a 0j. Now remember, in the 2 by 2 case, the forward product we left alone, but we subtracted the product on the backward diagonals. And we would do the same thing here. This arrangement here tells us that we have everything from the forward product as it is. So we have 0i plus 0j plus 24k. Some of these could have negative signs if we have negatives in our matrix, right? I don't have any negative entries here, but we could have negatives here, in which case you'd have minuses. You just keep track of whatever signs you have. And then you subtract the sum of the entries going back. So that's that 0k plus 0i plus 0j. Or alternatively, if you don't want to group things with parentheses, you could just take this plus this plus this, minus that, minus that, minus that. So you switch the signs as you go, whichever way you want to do this. Now again, we have a lot of zeros here, so for better or for worse, this all simplifies away. We get the 24k. And that is the same value of the cross product that we got from before. And the magnitude of that gives us the area of the parallelogram 24. Now, I should mention, we got 24k on both of these. Remember that we were thinking of this parallelogram as existing in the xy plane within the xyz space, within R3. So if you think about, I took 6, 0, cross 3, 4. So thinking about the right-hand rule, hold up your hand if you need to, and extend your fingers towards 6, 0, and then bend them towards 3, 4, and your thumb, in order to do that easily, your thumb would then have to be sticking out of the screen, right? So if this is in the xyz plane at the origin here, the positive z-axis would be coming up toward you. And that is at 24k. So you'd have a vector coming towards you with length 24. And it's that length that tells us the area. If we took the cross product in the other direction, 3, 4 cross 6, 0, we would have the same magnitude, 24, but now by the right-hand rule, that would be a vector going into the screen, away from you, and that would be the vector negative 24k. Same magnitude, opposite direction. But again, when we take the magnitude of that, that still just gives us 24. Magnitudes of vectors are non-negative. Okay? So those are 2 ways of computing this by the determinants. If you are watching this video at this point in the notes and haven't gone on yet to the algebraic properties, probably stop now and come back to this later. But if you have read the following subsections that talk about the algebraic properties of the cross product, and also the document I posted about using those to compute cross products, then you might want to use that third method, in which case we have, again, so we had the vector 6i crossed with the vector, 3i plus 4j, right? And using the algebraic properties, we have 6 times 3 is 18, times I cross I, plus 6 times 4 is 24, times I cross j. Now, I cross I, any vector crossed with itself, or more broadly, any vector crossed, or the cross product of any two parallel vectors, is the zero vector, all right, because the angle between them is 0. So if you think of the geometric characterization, we have sine of 0 is 0. If you think of the other geometric characterization in terms of the area of a parallelogram, the two vectors I and I would define a degenerate parallelogram. There is no area contained in that. The area is 0. You get the idea there. If you've finished the section and you know about torque, a force applied in the same direction as the radius will have 0 turning force. You get the idea. Now, for I cross j, for algebraic and geometric reasons, I cross j is equal to k. I talk about that in the document I posted, and that's also discussed in the textbook. 18 times the 0 vector is just the 0 vector, so this is 24k. Again, with a little bit of practice, we can kind of wrap this up into fewer steps. What made this so short in this case was how many components were 0, or in other words, how few non-zero components there were. When you only have, one non-zero component in one vector and one or two non-zero components in another vector, the algebraic technique tends to be quite fast. When you have more, if you have 3 non-zero components in each, then it's a little bit more of a toss-up as to which one you use. It's more a matter of personal preference. Most students tend to prefer the determinant techniques, so I will usually use those in the examples that I write out. I can also work through those with less space by sort of mentally arranging things, so I'll often do that. But it is good to know these algebraic properties as well. But again, the point is, through either of these 3 methods, we get a cross product of 24k, that is a vector coming out of the screen towards you with magnitude 24. And when we take the magnitude of that cross product, that magnitude 24 gives us the area of the parallelogram. And again, of course, this was a parallelogram problem, but recall that the area of a triangle is 1/2 base times height, because whenever you have a triangle, we can imagine extending that triangle into a parallelogram. So the area of the triangle is 1/2 of the associated parallelogram. So we also use this technique to find the area of a triangle that is just floating in 3-dimensional space someplace. We take the vectors describing any two sides, take the cross product, find the magnitude of that. That's the area of the parallelogram. Take half the magnitude. That gives the area of the triangle.